Hey, STEM team. So this week's challenge is going to involve a construction company that's digging out a foundation for a new home when they discover what appears to be human remains. And so instantly, there's going to be other people that are interested in this discovery. The police, for instance, are going to be worried that these human remains might belong to a victim of a crime. And groups like indigenous groups or archaeologists are going to be worried that the bones might belong to some sort of ancient civilization, that they might be disturbing a burial ground if the construction were to move forward. And so the question that we're going to address this week is how scientists figure out how old remains are. And so the answer is a process called carbon dating. Which scientists can use to figure out the age of bones by looking at the carbon atoms that are inside of them. And so what makes carbon dating possible is the fact that carbon atoms come in different forms. The most common form of carbon is an isotope or a version of carbon called carbon-12. And this isotope of carbon gets its name from the fact that it has 6 protons. That's what makes this a carbon atom. But also 6 neutrons in its nucleus. And so altogether in its nucleus, there are 12 units of mass. There are 12 different particles. And so when we say that this is the most common version or isotope of carbon, it is extremely common. 99% of all carbon on Earth is the isotope carbon-12. It has nuclei that look like this. However, there is a much rarer version of carbon called carbon-14. This carbon also has 6 protons. That's, again, what makes this carbon, is the fact that it has 6 protons. But in addition to those 6 protons, instead of having 6 neutrons, it has 8 neutrons. It has 2 extra neutrons, which give it a little bit of extra mass, the total mass now in its nucleus of 14 mass units instead of 12. So it's a little bit heavier version of carbon. In this version, when we say it's extremely rare, it is extremely rare. Out of all the carbon atoms on our planet, about 1 in every trillion carbon atoms is a carbon-14 atom. That said, to make our math a little bit easier today, we're going to round that up, and we're going to say approximately 1% of carbon on Earth is carbon-14. So where carbon-14 comes from is our atmosphere. Our atmosphere is mostly nitrogen-14. It's mostly nitrogen atoms with 7 protons, making them nitrogen, and 7 neutrons for a total mass of 14. And when a nitrogen atom gets hit by cosmic radiation, when it's up in the atmosphere and it gets hit by radiation, it's possible for that nucleus to go through a version of decay in which one of its protons, as it gets zapped, changes into a neutron. And so we'll show you a quick video of that here. Okay, oh, there it is, getting zapped by the cosmic radiation. And then here's a little clip of that. Okay. There you go. Appreciate. Wow. Yeah, look at that. Very high production value. We're going to watch that one more time. Here we go. Watch this nitrogen nucleus get hit with cosmic radiation. Here it goes. Wow, did you see that proton change into a neutron? Okay, so doing the math on this, when that proton changes into a neutron, let's click forward here, it now is no longer nitrogen. Nitrogen, by definition, has 7 protons. And it just lost one. So now it's a carbon atom instead with 6 protons. However, it still has a mass of 14 because it didn't destroy the proton. It just changed it into a neutron. So that's where carbon-14 comes from. All right, now the thing with this carbon-14 in the atmosphere is that it's constantly getting absorbed by plants during photosynthesis. So plants are absorbing carbon-14 from the atmosphere. And us as humans and animals like us are eating plants. So what that means is that if you were to take a sample of our carbon inside of our bodies and just look at, a swath of carbon atoms inside of our body, you would see that a very small percentage of our bodies is in fact carbon-14. Most of it is carbon-12 again, but a small percentage is carbon-14. And again, we're going to say in our class, we're going to round up and say that's 1%. Again, 1% of the carbon in our bodies ends up being carbon-14. But now here's the thing with carbon-14 is it's not a particularly stable nucleus. It is relatively unstable, and given enough time, it'll actually decay back into nitrogen. And we'll show you a video of this process. It's literally just the reverse of what happened in the atmosphere. Okay, check that neutron out. See how it changes back into a proton? And so what that means is that while we're alive and we're constantly consuming carbon from the plants that we eat, about 1% of our carbon is carbon-14. As soon as we die, okay, and we stop taking in new carbon sources, the few carbon-14 atoms that we have inside of us, they're going to start changing back. Now, this is a slow process. Okay, carbon-14 has a half-life of 6,000 years, which means that if we waited 6,000 years after our little caveman friend died, if we waited 6,000 years, half of these carbon-14 would decay back into nitrogen. And so if we were to take a sample of carbon from the skull that was 6,000 years post-death, we waited 6,000 years, we would see that, again, half of that carbon-14 would have decayed. It would be gone. And so every 6,000 years, these atoms go through another half-life. So if we waited another 6,000 years, that's 12,000 years total now after death, we would see that another half of the carbon-14 atoms would have decayed back into nitrogen. And so what's cool about this process is that scientists have figured this out and can now use the percentage of carbon-14 inside of a bone in order to approximate how old it is, how many years post-death. Okay, again, that's because while a creature is still alive, while a living animal like us is still alive, it's 0 years since its death, we know that it starts with 1% of its carbon being carbon-14. After 6,000 years, half of that would have decayed, and it would only have half a percentage of its carbon be carbon-14. And another 6,000 years, half of it would decay again, and so on and so forth. Every 6,000 years, half of its carbon would decay and decay and decay, until eventually you hit a point around 60,000 years after death in which there's just so few carbon-14 atoms left that you aren't able to use this process anymore accurately. You can't get an accurate assessment. And so that's what you guys are going to be doing in your challenge today. You're going to be looking at the atoms in a couple of bone samples. And let's say, for instance, you discover that out of all of the carbon atoms in the bone sample, 0.25% of them are carbon-14. What you can do is you can kind of work backwards and say, all right, well, we know that they started their lives while the organism was still alive at having a carbon-14 percentage of 1%. But over 6,000 years, half of the carbon-14 decayed to 0.5%. And by the time that it had decayed to 0.25%, it must have taken 12,000 years for that to occur. And so the samples you'll be testing might be different, but that's the general process that you'll use. The kind of the ability to think backwards and figure out, well, how long must it have taken in order for this bone to reach the percentage of carbon-14 that it's currently at. So that's it. Look forward to see your guys' work on these challenge problems. Best of luck.